Good day, and welcome to Africa Teen Geeks. This is a STEM digital school. If you are just joining this class, this is a grade 11 physical sciences. Today is the 24th of July 2020, and my name is Nonkululeko Matondo. Today, however, we are doing the term 3 assessment memo. As you guys remember that yesterday, we did start off with our assessment, and we did our assessment, which was basically for 45 minutes. And I hope that everybody was able to do it well and could understand what was going on in that assessment. Okay, so we wrote a test. The first question that we had to do with multiple choice. Okay, so on our multiple choice questions, the first question that we had stated that choose the correct answer. So you had to choose between A, B, C, or D. So now they ask, which one of the physical quantities has both magnitude and direction? So is it A, mass, B, distance, C, time, or D, acceleration? What is the answer here? Yeah, it is acceleration, right? Acceleration has both magnitude and direction. Okay, so it is D. So when we came back to our 1.2, it says in the diagram below, an object of mass m is held at rest by a string passing over the frictionless pulley. The mass of the string is negligible, so we neglect the mass of the string. The only important one is this one here. So the magnitude at P will be equals to, what will it be equals to? Will it be A, mg, or B, mg sine 45, C, half mg, or D, mg tan 45? And our answer is going to be number A, which is mass times gravity. Okay, there it is. It's mass times gravity, which is means it's A. And then we move on to our number 3. It says the velocity time graph below shows the motion of a car along a straight horizontal path. So A, constant frictional force acts on the car as it moves. So here you have it. Here's your car, and it's moving at a certain time, but at a certain velocity, and time versus velocity. Okay. So they want to ask, which one of the following statements best describes the magnitude of the force exerted by the car engine from T0 to T2 seconds. Okay. So is it A, it remains constant, B, it increases and then remains constant, C, it decreases and then increases, or D, it remains constant and increases? In my case, I believe that what's happening here is it remains constant. It should be number A, which says it remains constant, because the time here, as you can see, the time is constant. The only thing that is increasing is the velocity. The velocity is increasing from a negative velocity to 0 to positive velocity, but the time stays very constant. Okay. So we move to number 1.4. It says two trolleys A and B of mass M and 2M respectively are positioned as shown with a compressed spring between them. So there's a compressed spring between them. We've got mass A and mass B. So they ask, if the force exerted on the spring on trolley A is F, then the force exerted on the spring on trolley B is, it should be F, right? So it's also F. So whatever force is exerted on this one will be the same force exerted on this one. So this one will also have F as a force. Okay, so these are our answers, and I hope that you all got them right according to the questions that we did. So now we're moving to number 2. Number 2.1, it says, state Newton's law of universal gravitation in words. And number 2.2 says, a man weighs 800 Newton on Earth's surface. How far above the Earth's surface will the weight reduce to a quarter of his weight on the Earth's surface? So let's start with number 2.1. Let's state what is Newton's law of universal gravitation in words. It says that every body in the universe attracts every other body with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Okay, so that is the law of gravitational universal gravitation. It says every body in the universe attracts every other body with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their masses. So remember this formula, guys. Is this formula that says F is equals to G m1 times m2 divided by d squared. Remember is the one that we said it's very similar to the Coulomb's law, but in this case it uses different. That one is the size of the charges. This one is the size of the masses, and there you've got the square radius, and this one is the square distance. Okay, do you remember that part? Well, I hope that you do. So let's move on to number 2.2. It says a man weighs 800 Newton on the Earth's surface. How far above the Earth's surface will his weight reduce to a quarter of his weight on the Earth's surface? So now we start by explaining what we have. It says, let the height above the Earth's surface be h. Let r be the distance from the center to h. So it will be the radius. Okay. So now we're going to say, now we know the Earth is 800 Newton and the FG is a quarter. They said it's a quarter of his weight, which means it's going to be 800 divided by 4, and that is going to give us 200. So we've got the force of the person, the gravitational Earth, and the force of the reduced quarter of his weight. Yes. So this is where he's on Earth, and they said let the height above. This is the height above the Earth, and this is the height on Earth. Okay. So here we have it. So now this is what we have, right? They say when the person is standing on Earth, they are 800 Newton, but now they move above the Earth. So how far above the Earth have they moved for them to be a quarter, which is 200 Newton that we see over there? So now we're looking for this H here, okay? So which means that we'll have to find the new radius. So we have this radius, we have to find that one, okay? So let's move. So now we start with the force of gravitation of the Earth, which is equals to 4 times FGH, right? Remember we said it's a quarter, so it's 4 times when you take the 4 to the other side. Okay. So now you put your equation, which is your G MME divided by RE squared, which is just what we've explained. Remember that this is the equation according to the definition of gravitation, the universal, the law of universal gravitation. Okay. And then we do the same thing on the other side. So this, we have the R, we have the M's, and we have the G, equals to 4 times the GMME, but here we divide by RE times H plus H. So it's the distance from here to here plus the distance from here to here. And this is what we do not have, right? So after that, this GMME and this GMME are both the same, right? So we can cancel them out. Okay, and after we cancel them out, we're going to be left with 1 over RE squared equals to 4 times RE plus H squared. Okay, so once you have that, then you are done. You've got all that you need because you do have your RHE. You can cross multiply them to each other, and our H, which is equals to RH3, will be 6.38 times 10 to the power of 6 meters. Okay. So that is one way to find it. But now there's also another. This is a simpler way to find this answer right here. But there's other ways to find it as well. In this case, we're going to say if F is equals to mg, 800 times 9.8, and then we find the mass, right? This is going to be 81.633. Thereafter, we're going to say 200 is equals to 6.67, which is the mass of this G, times 5.98 times 81.63. Okay. And that we're going to divide it by r squared. So our r squared is going to be this, but this one is a longer method. I think it's always better. The shorter the method, the better, the less mistakes that you make. So I think this one is the one that is more appropriate for you guys to do. Plus, it's simpler to understand, right? Okay. So now we move on. Okay, I'm just trying to go to the next slide so that we see what is our next problem. Okay, so now we're moving on to the next part of our assessment, which was electrostatics, right? So what they say here is they say that two identical small charged spheres, which is A and B, on isolated stands are placed at a distance x meters apart as indicated on the diagram. So the charge on sphere A is minus 5 times 10 to the power of 6, while the magnitude of charge B is unknown. Okay, so that's the tricky part. So we do not know what is the charge here, and we do not know the distance because the distance here is x. But what we have is the charge of A. Okay, so now the following diagram illustrates the electric field pattern around sphere B. So this is our sphere B here, and it's got, you see the arrow direction. The direction is going inwards into the charge B. So what they asked was is the sphere B positively or negatively charged? What I can say just by looking at it and from what we've learned in our theory class is that this is a negatively charged, because remember the negatively charged is the one that takes in the electric field, and the positively charged is the one that gives out electric field. Okay, so let's see. You see it's negatively charged. The field lines are moving inwards into sphere B. That's why it will be a negatively charge. Okay. So number 3.2, they ask the charge sphere A and B are allowed to touch and then are moved back to their original position x meters apart. The charge on each sphere after contact is minus 3 times 10 to the power of minus 6. So what they want to know now is calculate the original charge on sphere B before it made contact with sphere A. Okay, so we come here. So we're going to start. There's two options that we're going to explore getting this answer. Okay, so now using the law of conservation of charge, we're going to say the charge before contact is equals to the charge after contact. So the sum of the charges before contact is equals to the sum of charges after contact. So here we know that it for charge A, it's minus 5 times 10 to the power of minus 6, but we do not have the one for charge B. And then on the other side of the equation, they told us that, remember what they said here. They said the charges on each sphere after contact is minus 3 times 10 to the power of minus 6. So it means that they both have the same magnitude there. So now you've got everything that you need, and you are looking for QB. So charge B will be equals to minus 1 times 10 to the power of minus 6 column. Okay, Do you see that it's much simpler now, this method? Because just knowing the charges before is equals to the charges after. But now we also have option 2 that you guys can also use, which is equals to Q is equals to charge A plus charge B divided by 2. So the charge, we know that it's equals to minus 3 because it's one charge, okay? One charge is equals to um, minus 3 times 10 to the power of minus 6. That is equals to minus 5 times 10 to the power of minus 6 plus QB divided by 2. And ultimately, you're going to make QB the subject of the formula. So they're both simple equations. You can try them both, and you can always try to use them both to see which one works better for you. Okay. So we move on to the last one of number 3, which is number 3.2.2, which says which of the spheres A or B lost electrons upon contact, and give a reason for your answer. Okay. So there is one that loses charge. So positively marking, it says it's going to be A. Why is A losing charges? Because it has an excess of electrons, or it has a greater excess of electrons than B, or it has more electrons than B. So it ultimately will have more charges, because you see QB has minus 1 and QA has minus 5. Okay. And besides, we always know that the positive charge is the one that gives out electric charges. Okay. So does that make sense? So let's continue. We still have a long way to go. It says on number 4, 2-point charges of magnitude plus 5 and plus 8 are placed a distance of 0.25 meters apart. Okay. So these are, it's also charges like the other one that we had, but a different scenario. Okay. So now they want to know, use Coulomb's law to calculate the magnitude of the force of repulsion that the charges exert on each other. Why is this a force of repulsion, guys? There's only one reason why this is a force of repulsion, because these two charges are both opposite. So, I mean, they're both the same. So remember, like charges repel, unlike charges attract. So in this case, we've got two charges that are both positively charged. So that's why it is, they're saying here, the force of repulsion. You need to be able to understand this, because sometimes it can confuse you. You can find yourself asking yourself, what does force of repulsion mean? But if you understand your concepts and why it can be a force of repulsion, then you will understand that all you have to do is just calculate the force using the Coulomb's law. Okay. So they say R is a point on a line. Okay, no, we still come. Let's do number 4.1. So here we have it. It says force is equals to Coulomb's constant, which is the standard 9 times 10 to the power of 9, times the Q1, which was given, and the Q2, which was also given, divided by 0.25, which is the radius, and we square that, and that will give us 5.76 newtons. Okay, so this one was quite a simple question. So they say here, R is a point on the line joining two charges, a distance of x. So now we've got an R, right? It's a point here. So this is the line between the two charges. So R is placed here, right? So, and it has a distance of x meters from the 8 UC charge. So such that the net electric field at point R is 0. So now they want to know from 4.2, define the electric field at a point. So basically now we're going to be defining what is point R, because point R is a point in the electric field. Okay, so they say here the electric field at a point is the electrostatic force experienced per unit charge placed at that point. So there's our charge placed at that point. Okay, so it's the force per unit charge, per unit positive charge placed at a point. Yeah, so it's a force. So basically, that's what defines this R that we have right here. Okay. So number 4.3 says, show that the distance x is equals to 0.14. So what's nice about this question is that they've given you the answer. So whatever you're going to calculate, you're going to have to find this as the answer. So this 6 marks, you can easily get it by making sure that you calculate until you find the right answer. Okay. So you remember how we calculate our electric field? If we want our net electric field, we need to calculate the individual electric fields first and then add them together to find the total, the net electric field. Okay. So here we have it. It's going to be the one of plus 5 coulomb and the one of plus 8 U coulomb. Okay. And then here it's going to be divided, and then you've got 0.25 minus x, right? Which is from this 5. When we want the distance here, the distance here is equals to 0.25 minus that distance A. Then we'll have our distance from the 5, this charge, to the R point. And on this side, our R point is the distance there is x, right? So we've got two equations like this now. So now we're going to equate them to each other, because remember what they said here, guys. Must always be clear of the answer. They say R is at the point in the line joining the two charges. The distance of x meters from the charges is such that the net electric field at point R is 0. Okay, so what does that mean? It is that the E net is equals to 0. But our E net at this time is equals to this and this, right? So if you can check here, that's why we equate them according from different sides, because this one is 0 and you can take this one to the other side. And then when you substitute these two, you can cross multiply this 2 and it will give you your x. Okay. Are we good to go, guys? I hope that everybody understands and is clear on now how to calculate electric charges at a point, and electric charges in your system. Okay. So now we move to electromagnetism. Remember, guys, I told you guys that for electromagnetism, we're only doing theory part for this year, and that is according to the CAPS ATP amendment schedule that they've made. Is that for electromagnetism, we won't be doing calculation whatsoever. So here we can have our first question, which says 5.1. State Faraday's law of electromagnetic induction in words. Okay. And that is the electromagnetic induction states that the magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change in the magnetic flux with the conductor. So the magnetic flux and the induced EMF, they are directly proportional to each other. Okay, so it means that if the EMF increases, the magnetic flux will also increase. Basically, that's what it means. They move at a rate that is proportional to each other. So now they ask, state that okay, the direction of the induced current is viewed from above. So state the direction of the induced current. Choose the clockwise or anti-clockwise. And in this case, it's going to be our anti-clockwise direction. Okay. And then we move to, because here they said a bar of magnet is dropped vertically downwards through a circular conducting loop as shown, and EMF is induced in the coil. So now we move to 5.2. It says, explain why an EMF is induced across the ends of the coil. Okay, across these ends of the coil. This is the coil, right? So the EMF is induced across the ends of the coil. So here it says the falling magnet creates a changing magnetic flux in the coil. An EMF is therefore induced. Remember from your theory part, guys, when we spoke about how is EMF induced, there's two ways. It's either the coil moves towards the magnet or the magnet moves into the coil, completing the electrical circuit. Remember, guys, we spoke about these things. So because it's falling, it's moving into the coil, and it creates a changing magnetic flux in the coil, and therefore the coil induces EMF. Okay, so okay, so now we move to question 6, and question 6 states that now is the application of the Ohm's law. It says here the circuit below consists of 6 ohms, and a 15 ohms resistor connected in parallel and unknown resistor R, okay, in series. So basically, this is our parallel branch, and this is our series branch. It's not a branch in this case because there's only one series resistor, but you can already see what is going on here. An ammeter, which is this one, a high resistance voltmeter, which is this one here, a closed switch, which is this part here. This is a closed switch, guys. Our, and a battery, this is our battery, are connected as shown. The resistance of the battery and wires can be ignored. So this is our wire. This that is connecting all the components together is a wire, and it's the one that carries the electric current through this circuit. Okay. So things that you need to know is that this V here, it's not part of the circuit, right? This is an instrument used to calculate the voltage across this resistor. So this does not really form part of the resistor. It's just an instrument that you can attach to calculate the volume that is there across this resistor, right? And this ammeter as well. This one, it's an instrument that is used to calculate the current that is flowing. So these two, they don't play, they don't affect anything in the circuit. What they do is they only measure what is already within this circuit. Okay, so make sure you understand the part of a voltmeter and an ammeter. It's basically just a measuring instrument. Okay, so they say here the total power dissipated in the parallel part of the circuit is 50 watt. So 6.1.1 says define the term power. Okay. So um, I'm just trying to find my answers. Okay, sorry guys, I'm just trying to see my answers here because I can't seem to find what I'm exactly looking for. So you know what I'm gonna do? I'm just gonna go to the text to the problem here so that we can find what we are looking for, because I think there must have been something that I did not do right. Okay, sorry about this, guys. Okay, so basically I'm just trying to look for our problem because I don't know, I think something just went wrong. So I'm just trying to find it. You see, guys, I made this paper out of an examination paper. So you guys need to make sure that you study your exam question and you know how to find your answers and how your questions are going to be asked, because you will honestly never know how the questions get to be asked, especially in an exam. So always make sure that, no man. Hmm. Okay, guys, you know what? Because our time is up, I think we'll finish this problem on Monday, okay? Then I'll have the proper things in place for this because it seems like I might have taken a different question from a different paper. So I'll have it on Monday. But for now, guys, I hope that everybody has gotten the right answer so far, okay? And to show that you guys understand what is actually happening with regards to the electrical circuit. So we'll finish up the application on Monday. And guys, thank you guys so much for a beautiful classroom. This was a term 3 assessment memo. My name is Nonkulego Madondo, and thank you guys so much. I am your physical sciences grade 11 teacher. Thank you, and please have a great afternoon.